It wasn't live, so now it's live.
Okay, now how do
Sorry.
Oh, there we go. Stop sharing.
Wasn't live, so now it's live. Yep,
Okay.
my mistake. All right.
To answer your question about my my avatar, I think it's either on Gravatar or one of the others associated with the email address that I use to log into the to Jitsi.
I believe it's Gravatar.
To answer your question,
Okay, so
about
Gravatar is one more thing
my
to worry
avatar.
about.
I think
And somebody who has the YouTube running needs to mute the YouTube if they've got the Jitsi as well.
Yeah, I generally recommend not using your speakers for Zoom or Jitsi meetings.
That too. But if somebody's going to monitor the YouTube while being on the Jitsi to relay questions or chat or whatever, yeah, it needs to be completely muted. You don't have two headphones.
Yeah, good point. I see Joshua's question. I'm not familiar with XPRA, but is anybody familiar?
Kurt?
Yeah, I think I know who we can refer this to. Maybe even Michael. But yeah, that sounds like something that they do in queuing big jobs on big NVIDIA clusters. So I'll ask.
Okay. Okay, so I posted the live stream link to the IRC, to the announcement analyst, and to the Blue homepage.
Okay, that sounds good. Let me refresh it. Yeah, I got it. Good.
Okay, this video is
Interesting. I had an email earlier from John Boland, and He said when he clicked on our Jitsi link, it came up in Russian. It comes up fine with me and stuff like that. But
I wonder what he's got in his user profile.
yeah, I have no idea.
I've been seeing that if you're using Surfshark, actually.
So is that Russian spyware?
Yeah, apparently so.
That might be a warning.
Wouldn't Jitsi just depend on the user agent language preference?
If it's doing it right. If it's doing it wrong, it's depending on something else, like how the software was last compiled.
Live streaming is on.
Hmm.
We can all start talking at once too.
Yes, but it doesn't work well.
I just discovered the Vosk speech-to-text engine, which is made of a free model and free open source software. And I was thinking about playing around with that for making automated transcriptions of some podcasts. Has anybody tried it?
Who makes the model?
I'm pretty sure Vosk came out of the CMU Sphinx project. I don't know exactly who made the model, but it came from somewhere in that circle.
This is for text to speech or speech to text?
For speech to text. And the use case that I have is take a podcast that's already been published and make a new feed out of it and maybe watch the existing podcast feed and automatically download new episodes, transcribe, and make an RSS feed of the transcription.
If
I would
that
be
worked well,
very
I would-
interested in your ability to get that working on a Linux machine.
I would
Yeah,
be
and-
totally amazed if it works well. People who've used commercial transcription services that have found that the automated ones work fine for business meetings and terrible for anything technical.
Yep. Well, the only thing to do is just download it, try the samples, and play around with it. If you go to the Vosk GitHub repository, there are example scripts in a in an example folder that one of the example scripts is take an arbitrary audio file and convert that to SRT captions. So I'm actually going to try that tonight, just try a couple of different podcast episodes and see what I get. And if it works well enough for government work, I'm going to try making a service.
Bad captions are better than no captions, but
Yeah.
It reminds me of one of the other technical meetings in which the humans did not transcribe Unix correctly.
Yeah. So if you're going to be searching for technical names inside of a transcript, you might not get very far. But if it's, for example, a news-related podcast, you might be able to find some, get some hits if you search through the transcripts.
Yeah, that would be interesting. It'd be great if you presented on it. In the next.
Oh yeah, sure. Don't get your hopes up, but I will let you all know if I have some result that I want to share.
So I've spent some time looking in voice to text in the FOSS ecosystem. So I've used pretty successfully the ones that Microsoft eventually bought out. I've been less successful with the Sphinx and those. As far as real time, I don't have anything that's running in FOSS, so I'd be very interested in any form of real time processing. You can also look at, for non-real time, Mozilla had a, I think they called it Deep Speech. It's probably right on GitHub, where it uses GPGPU calculation. But that's not real time. Although it predates the RTX stuff. So you may actually be able to have it working with the 20 series RTX accelerators. So let us know.
Yep. And I just dropped a link in the chat to the install page in the documentation to give you an idea what it looks like. And it does, the examples allow for real-time speech to text and also a static file speech to text. So I'm going to try it out, see how it goes. But if you don't hear from me, I couldn't get anything good out of it.
All right, thanks.
All right, and the project seems to be, the Vosk as a project on GitHub is less than a year old. I have no idea how old the model is, but just looking at the instructions in the demo, it looks like it's easy to set up to try to get something out of it. Anyway, end of comments.
I think we should start the first speaker now.
Yeah, we could start the first speaker right now.
Who did we say was going to start?
Seth.
Seth? Is Seth here yet?
All
There
right.
he is.
All right. Hopefully you can see and hear me.
Oh, yeah. Okay.
Yep,
Yes.
loud and clear.
Okay. Excellent.
So,
Great. So I am in New Hampshire in a cabin in the woods. So I put these slides together yesterday and have not gone through them. So we'll see, how they work. But please, feel free to ask questions while I'm going through them. Happy to make this conversation. Also, apologies for the camera angle. The camera in my computer is in the keyboard, so it's got the nose cam. All right, so. All right, so can you guys see my slides?
Slides look good.
Slides look good. All right. So, yeah, thanks for having me. I think I've been to a few of these meetings. I think in person at MIT a couple of years back. this is a project that I've done over the last few months that called Birdbox, all on Raspberry Pi. So I think it counts as a Linux project. If you would like to go to the website right now, there's the URL. You probably won't see much since it's dark out. But yeah, so we're going to tell you about Birdbox. Basically, this has been my COVID project. So a little bit about me. First of all, I'm Bob Frankston's son, born and raised in Boston, the background in neurobiology. Currently working as a research scientist for the U.S. Army, and I have zero background in ornithology. So if any of you guys have any backgrounds, I'm all open for tips. All right, and yeah, if you have any questions or want to contact me after that, here's my email. So just to give a brief overview of the slides, so sort of go over the motivation about the project. I want to go into a little bit about the build, sort of the external bits and the hardware, and then go over the software as well, and sort of leave a little bit of time to go over the final results and any discussions that may arise.
Live streaming is on.
All right. So as I was mentioning, this is basically my COVID project. I think we're all stuck at home, needed something to do. And this sort of came out of, conversations that I was having with my family and sort of interests that we are all having. So around the time of COVID, probably a little bit before, my parents started getting into backyard bird watching. So on the left, this is actually one of the books I gave my mom to help her get into bird watching. Very funny book if you've never read it. But basically, the sort of the question arose, wouldn't it be great to know, which birds were coming to the backyard and how many and when? And this was really sort of the origin of Birdbox. And today I'm going to be talking about sort of the final iteration of Birdbox. Technically, I think this is Birdbox v3. There are plenty of versions that came before, but I don't think we need to go through all of the lessons learned. If there's any interesting lessons learned, I'll try to cover them. So really, what is Birdbox? So it's a camera that's set up right now in my parents' backyard, designed to essentially live stream 24/7 video that both detects and classifies birds, as well as provide high-level bird statistics and serving them in a gallery to visualize the detected birds. That's sort of the high-level overview of sort of what Birdbox is, what Birdbox is meant to do. Sort of in a little bit more detail. So basically, it's hardware, software that, again, captures live video. The video is passed to an object detection model built using TensorFlow, boosted with the Coral chip, which I'll detail. Video frames are analyzed for detected birds. When a bird is detected, that frame is saved, and at some point those birds are classified so we can identify the species. And then finally, birds can be viewed live or in a gallery by species, as well as the high-level statistics. So the next few slides are really going to break down sort of what's written on this slide. So again, going after the build, the hardware, and the software. So this is Birdbox in the wild. This is a picture from my parents' backyard. On the left is the actual bird feeder, and on the right is Birdbox. So on the left, so with Birdbox, or excuse me, with the bird feeder being on the left, essentially there's bird seed and suet. Suet is, I've never heard of it, but it's sort of like it's a paste, it's like fat or lard that apparently birds really like. So it attracts a lot of different types of songbirds. On the right, so again, actual Birdbox, starting from the top, basically the bird box, or the brains of a Birdbox, is essentially inside a PVC junction box. Going through the middle, so basically the stake is both a 6-foot fence post and a 1x6 wooden post. The white thing, that's actually just a 4-inch PVC pipe, and it serves as a squirrel baffle. So essentially that, for whatever reason, the 4-inch PVC pipe is the magic number that squirrels cannot get their little arms around, and they can't climb up. So one of the big concerns about having essentially a big post like this in the backyard was, aren't squirrels going to climb it and jump to the bird seed and basically eat all the bird seed, and birds won't come. So far, based on my parents' account, based on my accounts, it's been 100% successful at deterring squirrels. So essentially, we've had no issues with squirrels climbing this. It's all posted in a big bucket. I spray painted it black for aesthetics, but it's one of those orange Home Depot buckets, and it's filled with cement. So essentially, this thing is not going anywhere. The whole setup without the cement is really not that heavy, but it did pose a challenge of how do you sort of post this so it doesn't lean over and without digging a big hole in the ground. Essentially, putting it in cement, solved that problem, and it really hasn't gone anywhere in the last few months. And I should say this has been up and running. I think sort of August, we really decided the project was more or less complete. So it's been running for a couple of months without going down and without being knocked down. And I should also say, there's electricity that's coming from the garage that's on the right, and that's just going right up along the fence post, and it goes directly into Birdbox, and there's a little cable gland that essentially makes a thing weatherproof. So, there's really been no issues with water so far. Granted, I have not opened it up. I'm not really clear what's going on inside right now, but the fact that I can actually ping it, that I can actually watch live video, pretty good indication that things are up and running. So a little bit of a closer view on the actual brains of the actual Birdbox. So on the left, this is the outside of sort of the completed box. On the right, it's opened up without any of the hardware in it. So on the left, so again, starting with a 6x6-inch PVC junction box, it's probably a little tight, but it gave me just enough room to put all the hardware in there. Figuring out how to make the actual lens aperture outside of the PVC box was actually pretty difficult. I went through a number of iterations, but right now there's a camera lens filter that I bought off Amazon for like $5. And there's a I think 55 millimeter step up. That's basically that's what the camera lens filter is screwed onto, and the step up is both glued and screwed in with those little plastic screws that you can see, and that's worked so far. Essentially, it's kept all the debris out and allows the camera full clear view out of the box. There's the 2-inch round louver. That's essentially allowing airflow. So if you open it up on the right side, so the inside view, on the left, there's that's essentially the camera aperture. That's where the webcam is facing out of. You can see the cable gland, so that's where the cable's coming through. Hopefully you can tell that. So that's basically an orange electrical outlet. The louver. So there's a louver, but there's also a fan inside of that. So that's essentially pushing the air out. For a while, especially during the summer, I had a real big issue with heat. So the thing would basically heat up and would turn off. So, I was basically could only keep it on for an hour or so. I had one of my mechanical engineer friends take a look, see if he can offer any advice. He said, you need airflow through the thing, through the Birdbox. So he suggested basically making these holes the ventilation holes. Ever since I've had put the ventilation holes in and we're forcing air out of Birdbox with the louver fan, I've had zero issues with heat. Even throughout August, no issues. Even when it was like 90s, in the mid 90s, high 90s. So that actually worked really, really well. That was one of the key problems I had issues trying to solve. But essentially allowing that airflow through. there's a there's basically a fan mesh for computers that's on top of the ventilation holes, and so far that it looks like that's kept bugs out. So no issues there. So the hardware, so using 8 GB Raspberry Pi 4. One thing I did splurge on, so the first 2 Birdbox iterations, I used the camera, the Raspberry Pi cam. While it's really good and it's really cheap and basically a cinch to get up and running, and especially it's really easy to serve it to get a live feed. The biggest issue I had was that it didn't have autofocus. So that made it a real challenge to get birds sort of when they were moving. As I was playing around with sort of the distance between Birdbox and the bird feeder. That just posed a number of challenges where at some point, I think my dad has actually pointed me to this. You can get really high-end like security camera. So this is basically a 4K camera, webcam that's really designed to be discreet and really small. I don't really care about discreet. I care about small. I did have, Logitech webcam in there. It basically took up too much room, and I was not able to fit everything in that 6x6 inch box. The really interesting thing that I added on pretty late into the Birdbox versions is the Coral. So the Coral USB accelerator. That's essentially an edge tensor processing unit, TPU. So it essentially allows you to do AI, edge computing AI, and essentially take all the burden off of the Raspberry Pi. While the Raspberry Pi is, pretty powerful GPU, I was doing a number of other things with it. And essentially, this allowed me to not worry about any of the resources on the Raspberry Pi and dump everything on the Coral USB. So that, it's what, $59. It's been pretty fun to work with. I highly recommend, picking up one and taking basically all the processing requirements off of your Raspberry Pi or, whatever microprocessor you're using. It actually also works with a PC. So you don't have to be using a Raspberry Pi for it. So I hope you forgive me. Unfortunately, I don't have a picture of all the hardware stuffed inside the PVC box. Like I said, I'm in New Hampshire. I wish I did have a picture. This is a picture of the Raspberry Pi and the Coral USB. Essentially, how it's set up. And you can also see that it's basically drilled into this PVC plastic sheet, and essentially that is the base that I used, and used little standoffs. So there's air circulating under all of this. It's essentially, it's not stuck to the bottom of the PVC box. There's air that's able to flow throughout all the components, as well as allow air to come through the ventilation holes. If you're interested in the Coral USB accelerator, essentially it uses edge TPU, which essentially allows you to run TensorFlow algorithms very, very fast, and offloading all of that work off of the Raspberry Pi or whatever computer you're using. It does get pretty warm, but I think that's usually not an issue, especially if you're not using it in an enclosed box. Let's see what else. Essentially it's a chip that's designed specifically for running AI. So the software, so everything's written in Python. I'm using OpenCV for basic image processing. Flask I'm using as a web app framework. So there are obviously issues with security. I'm not so worried. If you hack into this, good for you, I guess. Bootstrap to make everything look pretty. TensorFlow Lite, so that's essentially it's TensorFlow, but TensorFlow Lite, which is designed to work on small microprocessors like the Raspberry Pi, and it really does work pretty effortlessly. And there's a ton of resources out there to help you get started. Also using pandas to do some sort of light analytics with the data. So essentially there's the software architecture, there's two components. There's the detection piece and the classification piece. Currently, they're not working together, and the primary reason is because they both rely on the Coral chip. And once you spin up like a TensorFlow model with using the Coral chip, you can't run another model without, I guess, spinning down the Coral chip. Or at least I haven't figured out how to do that yet. So currently, it's essentially running as a detection app and a classification app. And if anyone on this meeting has any suggestions, I'm happy to listen to those, and I'd love to make this a little bit more seamless. So the detection app, it's pretty simple. Essentially on the top left, there's a camera, so that's my webcam. OpenCV is basically opens up a video capture to get frames. Each frame is then sent to a object detection model, a TensorFlow object detection model with Coral boosting the detection. I then use OpenCV to basically do some basic drawing onto the frame. So this is actually a frame from BirdCam. So on the top left, there's some frames per second. I'm actually getting 15 frames per second, which is actually really, really good. Without the Coral chip, I was getting about 1 to 5 frames per second. So, offloading a lot of that processing off the Raspberry Pi really does drastically improve your frames per second. So that was fantastic. On the top right, there's a temperature. That's the CPU temp. I was using that to essentially debug what was going on, why it kept getting shutdowns before I added the ventilation holes. Bottom left is just the time date. And essentially here is a really fantastic picture of a little baby cardinal. So the baby cardinal, so basically the object detection model is working. I think it detects up to, I don't know, I want to say like 100 different objects, essentially that it's trained on, and you provide it a text file that has all the objects you want it to detect. Bird is one of them. So essentially, I'm using a pre-trained model. At some point, if I want, I can retrain the model to be more specific and more accurate. But right now it's actually working pretty well. So this says it's a bird, 58% probability. So somewhat arbitrarily, but essentially 58% seems to work pretty well and seems to reduce a lot of the false positives. Essentially taking, if a bird is detected at greater than 50% probability, that frame is saved. And one thing that I found to be important is to reduce the amount of an image that the classification model is looking at. So within the green border, and actually this is something I didn't show in this PowerPoint, but I'm not saving the entire frame. I'm actually just saving what's inside of that green border. So I get a really tight cropped picture of a bird that's more easy to be classified than the entire picture. So that's one piece. Essentially, the frames are saved to file or to disk, so I can later do classification. But regardless, those frames are streamed live with Flask. So during the day, so right now, if you go to that website, you can see live frame. I'm not using any IR or anything like that. So, it's really best used during the day. Moving on to classification. So right now I have a cron tab task. Essentially every midnight, I shut down the website and turn on the classification app. Again, this is pretty sloppy, but it's what I was able to get working. And essentially it's working now. So until I find, another different reason to actually to change the scripts, I think this is good enough. Yes. All right. So essentially every day at midnight, I loop through all the bird pictures that were saved during the day. Each of those pictures are passed to the TensorFlow classification model. So again, Google was nice enough to develop a bird model. I think it does birds, bugs, and trees. But essentially, they are able to detect up to 900 different species. I think we're pretty safe, especially in North America, where most of the birds that are captured in our backyard are able to be classified. It often misclassifies it, but when it's a cardinal, for example, it's pretty damn sure. So in this case, this thinks it's a cardinal and 96% confidence. That's very accurate for this model. So if the species is detected with greater than 80% confidence, it's added to the image gallery, and those images are also served along with the live feed of the birds. So moving on to sort of the final result of sort of what we're seeing. So this is a picture yesterday. The pictures that I was showing you earlier are 1080. I've been playing around a little bit with resolution. This is 1920, so you can see the frames per second are a little slower. I may actually change back to 1080. So the Birdbox actually got knocked down. So we're just seeing the seeds. That's why the frame looks a little different in the previous pictures. But essentially, this is what you would see if you went to AZ.LT:8003. You'd see Birdbox. This would be a live feed. I'm not dumb enough to actually show the thing live. I've learned that lesson. So this is such a frame shot. It's all made pretty with Bootstrap. So essentially on the top you have live feed, you can look at all the classified birds, you can view by bird species, as well as sort of high level statistics, and then there's an about page that tells you a little bit more about the build if you're interested. And I'll probably add some of what I did today with these PowerPoints into the about at some point. If you want to look at the actual classification values for each bird, you can click on classified birds, and you can use the pagination feature, which actually took me a while to figure out. I was pretty proud of that, to build that into Flask. So in this case, there's a blue jay, 58% again, and 97% confidence. Below, you can see the frame for grackle. Grackle, I've never heard of a grackle until I started doing Birdbox. So, that's one thing I learned throughout this process is grackles are super, super common and they're super annoying. You may confuse them with crows. They're not, they're grackles. And yeah, they're pretty annoying and they eat all the seeds. Here is an example of viewing the birds by species. So here's woodies, woodpeckers. I basically did the top. I wish that this was dynamic, but it's not. This is a static list of grackles, blue jays, cardinals, woodpeckers, sparrows, starlings, turkeys, titmouse, chickadees, or you can look at all birds. And you can click on these and it shows you a really nice big picture of each bird. And this is so this is pretty accurate. There's all woodpeckers here. Like I said, it's not always 100% accurate. So, at some point, I probably have enough data right now to retrain the model. But, I don't necessarily have the motivation to do it at this point. The high level statistics. So this has actually been pretty fun. So, this is playing around with pandas. I think these pictures, I formatted these pictures a while ago. At this point, there's a lot more birds than I had. So, I probably should reformat things a little bit. But numbers for birds. So this is through, I don't know, probably since July, maybe. So basically the total number of birds. So seeing, 1,400 grackles. I get this question a lot of, how do you know if you've seen the same bird multiple times? You don't. If Steve Bird shows up 3 times, I'm not going to know that's Steve each time. It's basically just a different grackle. But what I do is I group all the birds I've detected into 5-minute buckets, and essentially only pick one bird, like if one grackle per 5 minutes, with the idea of, Grackle probably stayed around for a few minutes and left. That way I'm not getting, sort of 120 Grackles in a 5-minute period. I'm just getting one. So I think that it's more accurate that way. There's probably more better ways to do it. But again, sort of this worked. So essentially here, common Grackles, and you can't really see that's overlap, but that's the blue jays and then European starling. Those are the top 3 birds that we've seen, and that tracks pretty well with, I think my observations and also what you would expect to see in the Northeast. This is actually a probably more interesting statistics. This is essentially a stacked bar chart by hour of the day, so 6 a.m. all the way to 6 p.m. And it shows sort of the number of birds per species that have been detected per hour increment. So as you can see, so the orange and the blue, so the orange is Grackle, the blue is blue jay. And, those are without a doubt the most common birds that we've observed. Blue jays do sort of seem to come earlier in the day, 6 a.m. There's definitely a peak at breakfast, so probably around 8 a.m. And then again around lunchtime, around 11 a.m. And then things trail off accordingly, as the day moves on. There probably one thing I have not looked at is sort of how the shift or how the decrease in the hours of daylight changes the species that come. Or if there's any correlation. So I think that's one thing would be interested in looking at. At one point, I did have an ornithologist actually reach out to learn more about this. So who knows? Maybe this talk should be something useful someday. So ending on sort of some of my favorite pictures that I've taken. This is that Birdbox is taken. This is fight or flight. I like it because they're both fighting and flighting. Kind of funny. And then this little sparrow sort of getting in there, trying to get the food while these grackles are fighting each other. Probably my most favorite picture, called the golden ratio. So we have a woodpecker, cardinal, blue jay, grackle, and lo and behold, it actually is the golden ratio. So who knows if they planned that or not? Probably not, but I still think it's pretty funny. And let's see. So yeah, I put some of the resources that I really relied on here. Feel free to reach out. I'm happy to provide any of those links. And that's it. Hopefully that was on point and interesting.
That was brilliant.
Excellent.
Yeah, it was very interesting.
Yeah, thanks, Seth. Can you send us a copy of your slides to post on the website?
What's that?
Can you send us a copy of your slides so we can post it on our website?
Absolutely. Yes. Yeah. So I see a couple of pictures or questions in there. To see Bob, you asked if I could use 2 curl chips. I probably could. We have 2 coral chips. I know you have one, so we could probably put those in Birdbox. I probably think there's a better software solution. And instead of taking the website down, I could probably put up a under construction or whatever instead of just taking the whole thing down. So yeah, I think there's a number of solutions there. It's squirrels. I've seen many squirrels. They're a pain in the butt. At some point before the baffle, we were getting lots of squirrels. I'm thinking about actually retraining the model to remove the squirrels, but essentially with the baffle, I haven't really had to worry about squirrels too much. So, yes, thank you.
Can you hear me?
Yep.
Okay. Have you looked into removing the background image? Because there's not going to be too much change. There might be leaves. But if you look at it over time with an LSTM or one of the temporal, in addition to your convolutional neural net that you're using for mobile, the mobile net database. You should be able to remove the background and get very clean images of the birds themselves, because they're actors essentially on a screen.
Yeah.
A mostly non-moving, so you can, there are segmentation techniques in image processing. I also wanted to point out there are ecology calculations for reoccurring individuals.
Oh,
so that
okay.
might be helpful for you.
Yeah.
So I can send you some of that later. But
yeah, that'd be
yeah,
fantastic.
it's interesting.
Yeah. Thank you.
Yes.
So are you saying remove the background in place of cropping out the birds?
Or in addition to.
Or in addition? Okay.
Yeah.
I was originally using Motion, Motion CONF, Motion Project. I'm not really sure what to call it.
Okay.
A lot of people use it with like for security projects with Raspberry Pi. They have a mask that you're able to use that was pretty effective, but using their video image software, I think, was kind of limiting, which is one of the reasons why I went to OpenTV. So yeah, no, I totally agree. Trying to get rid of that, the background statistically, I think would be interesting project.
It'll also save some of your later processing time.
Yeah. Excellent. Thank you.
So Jerry, I think we should move on to Bob, the next speaker. I'm actually was inspired by Seth's presentation, so I can probably repurpose the Herrick videos in context of TensorFlow. He's a big cafe guy, but now that I've seen what Seth did, I think we can probably revisit that. In fact, since I've got such bad bandwidth tonight, I can probably do it as a read ahead, like a YouTube video, and then we can just do Q&A, and I can just be here for audio. But I think I should really pass it on to Bob at this point.
Okay, Bob, are you ready to go?
Yes, I just need to find the right OBS camera. There it is. Okay, so there are two things. I was asked to talk about OBS first. How many people know about OBS? Well, your cameras are off. You can't get any feedback.
We don't see you.
Yeah, my camera's on now, so I'll just have my audience. You have to press escape and switch windows. Okay, so I guess I can't ask how many of you know about OBS, so I'm going to tell you about it. OBS is basically a video stream processing program that allows you to take video, instead of just going to your camera directly, you create a virtual camera and it has a canvas you can place things on. And you can do arbitrary audio, video processing. You can be arbitrarily complex. So I'm not an expert, so I'm just using it in the simplest case. So you notice, actually my green screen, I need to adjust a little. So I'm going to go to my green screen here, and you can't see this. So this is OBS. In the background is my other window. And you can see the problem when you show OBS on itself. Okay. So what it can do, you see that woodpecker? Oh, everything else just disappeared on me. So you see the woodpecker there? I'm busy trying to, I can just remove it. Okay, so that's a little less disturbing. And I can also now go to the green screen and filter and change a little, but won't worry about that. So before I continue, are there any questions about OBS? No?
What's that?
I'm just asking, are there any questions about OBS? Are people curious? Or if you know about OBS, please just do something in chat saying you already know about it. Okay. Either everybody knows about it and it's too stupid to answer, or nobody does. So I'll move on. I don't have my green screen why it's so acting like it is. So the other part of talk is on 5G. Now here, this is another area where we really want to really have a conversation because I want to understand sort of, I see 5G as marketecture. I'm not going to stick to the slides. I'll go through them if I have to. But marketecture is sort of, it's like Stephen Colbert uses truthiness. So marketecture is to architecture, sort of, it's basically, it's the marketing version of it. It sounds like science, sounds like engineering, but it's really marketing. And the reason I'm talking about 5G is I write a column in the IEEE Consumer Electronics magazine, you see there. And you should join, IEEE Consumer Technology magazine. We just renamed ourselves. But notice the magazine hasn't changed itself yet. Oops. Name change so hard. And I thought I explained the internet and everything. And then I see an issue which is all about how 5G is the future of consumer electronics. And 5G is actually the antithesis. So to understand what 5G is, I have this slide from Huawei. Okay. Yeah, it's fast lanes. It's everything that's the anti-internet. And that's the real point. I mean, this slide alone should make the point is you don't want it. It's an attempt to bring back the old phone system and special applications, but it really is vital. You have to understand why 5G must be the future, because the telecom industry faces an existential threat from the internet. It has no reason to exist. 5G is the story. If the children believe 5G, there's a future. We'll pay for things. So, I was thinking a lot about Hushaphone. Now, this is where I really miss not seeing raised hands. How many of you know about Hushaphone? I'll pretend that a few of you raised your hands and the rest are looking at me like, what is that? So Hushaphone was a box you put around your phone to make it quieter so people in the room couldn't listen to the conversation. And they were sued by AT&T because that destroyed the quality of their service. It harmed the reputation of AT&T. So, it went all the way to the Supreme Court and basically took the U.S. Supreme Court to say, you're allowed to put a box around your phone. And if you think about the idea, the phone was not something you used to play phone, that you owned. The phone was an instrument provided by the phone company to deliver a service. That was the high point of the old model. I mean, cell phones are similar to that. But this was really, very hard for people to understand. But it wasn't until 1968 and the Carter phone decision that you're allowed to own your own devices. Now, for those of you who remember Get Smart, that's not a shoe phone. That's an acoustic coupler for an answering machine. But you weren't allowed to. You had to buy answering machines as a service. But that's what telephone companies do. They sell services. But they made one big mistake. They did good engineering. Actually, colors aren't showing up right on those wires. That's supposed to be red, green, black, and yellow. And because the two-wire interface is so simple, they couldn't pretend that it would destroy the phone network. They actually claimed that if you hooked your own phone to the network, it would destroy the complete phone network. I mean, you wanted to destroy the phone network, you just bought a box of Captain Crunch cereal and used the whistle. That could destroy the phone network. Hooking up to the red-green cannot. So they lost that case. But you have to appreciate whole system engineering, that you're able to do TV in the 1930s because every element of the system was carefully designed to all work together. And the amazing thing was voice worked, even digital voice worked, that you're able to carry this analog signal all the way across the country. That's an amazing feat. So if they didn't control the telephone, They couldn't have done that. They did every element of the system. And that's sort of any new engineering system. The first version is carefully crafted and everything. This is what Apple does now. They built a whole ecology around the device, but you can't, if you fall out of their ecology, nothing works. So that's the positive reason. But the point is, eventually you learn a lesson. You learn that you can put your own device on the red-green interface. Now, they did get revenge. The cellular industry is so complicated and sophisticated. I mean, nobody can implement the cell protocols except the phone company. Well, maybe not. You have to remember, this is all done with 1970s technology. And for those who remember the Hayes modem, the AT protocol is at the heart of the cell phone. It's really just an amateur kludge. If you look at the protocols, they're just internet protocols badly done. But what has happened is today the telephony is just an app. So the whole premise of this has gone away. That's what 5G is supposed to address. The value is no longer in the network. I was going to use Zoom as an example. You write Jitsi or anything, none of that value goes to the phone company. So they've got a real problem. How do they make money if they can't sell your services? And that's what 5G is supposed to address. But 5G prevents innovation, oops, wrong window, because everything is built into the network. You have to have a special network and service for reaching. That was our charters. They can sell services again. What could be better? If people believe the nonsense, then they can make money. And that's the purpose of marketing. So I have a 5G Verizon Fios set-top box. It's amazing. What's amazing about it is there's no 5G in there at all. They say, yeah, you're supposed to buy a 5G internet service. We'll call it 5G. And the other part of it is there's no Fios there. Just it's a generic Android TV box. So the engineering reality is it's nonsense, but the marketing people label everything 5G. They put a stamp on it. And they said, please don't look at Wi-Fi 6. You know, that makes it too easy. So this is all dragging value, clawing value back into the network. And what's hard to understand about this is the concept of best efforts. How can you basically do a phone call without a phone company? How's that possible? So I've told the story in the past about radio packet networks, the Aloha Net, the sort of discovery of best efforts. The fact that we can use software and intelligent on computers and devices to do everything the phone company did without a phone company. And, that class I learned about it was interesting because Bob Metcalf was the kid sitting next to me, and he used those ideas to build Ethernet. If you think about the Ethernet in your house, there's no connection between the voice app and the network. All it just sees a raw packet. And that's because you have software that instead of relying on the network, because the old days was a dumb microphone, it's basically able to program around the limitation network retry, and we can basically do a video with an app and just works. But the key point is innovation such as voice over IP had to be discovered. They could not have been done by telephone engineering because you don't do things that are impossible. It was impossible to do voice over a jittery network, so why try? Now, it turns out the secret is they actually did it over analog international lines with long delays, but you have to pretend you don't know. The same reason we ban ultra wideband, even though we have a 25-watt radio at 2 billion miles away, still works fine. But these new but in the 1960s, there was a path-dependent engineering. If you wanted to do better radio, you got all the frequency and everything. If you actually want to get a job done and free to think, you can do ultra wideband. So there's an origin story in which Vocaltech discovered their users were using voice over IP. They did voice over the local network. The user doing voice over IP. So that's the extent to which it's unanticipated. And what's really hard to understand is that voice over IP works despite the phone company. There was no way to buy privilege, so they had to program around it. But more important, the phone companies were threatened by voice over IP, so they kept trying to make it not work, and it worked anyway. And Zoom, or I should change the slide to say Jitsi in this case, the voice is free. So why do we pay for phone calls? Why do we have a concept of phone thing? And if the more you look at it, the stranger it is, because whether people remember message units. That's the way phone calls were measured. Those message units were telegrams. Your phone call was measured in terms of telegrams. Just like today, a voice connection over the cellular network is mentioned in minutes, even though we no longer have on hook or off hook. But by using these terms, we preserve the past. So traditional engineering, you taught layers of dependency and everything. So the whole IEEE is traditional engineering. You carefully built every system because it was a whole system design. In order to get voice to work, you need every element to support voice to be designed for that purpose. That's what we teach engineers. In the real world, you got to solve a problem. It's a two-sided thing. You've got to look at the resource you have and decide which problems to solve. It turns out there's so many things to solve that if you find solutions with the resources you have, you get to basically a very efficient thing. If you have to solve a problem despite everything, you're going to do a lousy job and it probably won't work. That's why so many big city engineering projects fail. You don't want a smart city like 5G. What you want to do is build resources. With plenty of examples. One example I use is New York City tried to do a complex system which would put signs up when the next train is and everything coming. It spent many, many millions of dollars and it failed. Later, if you just have an API and generic connectivity, anybody can do this app, and we can not only display the signs, we show train routes, we do scheduling, because we've decoupled the system and have good system architecture. By removing the idea that you need separate infrastructure for each purpose, we enabled innovation, enabled creativity. And this is essential for the so-called Internet of Things, which is really connected things. You cannot do connected things if you have a paywall. If you're trying to make every wire a profit center, you cannot possibly have connected things because, there are no IP, and this is essentially intellectual property, circuitry in the chip to emulate a lawyer reading an agree screen agreeing. They can't argue about a billing thing when the billing is 3 levels down in the network. You don't even know it's there. So the fundamental concept of funding the network by selling services cannot work. One, we create the service ourselves. Number two is it's all decoupled, so you don't even know who is buying the service, who's paying for it. And it is not a new idea because it's not just sort of the best of its internet. You look at the failure of FireWire. It was too smart. So as soon as you got outside the design point, it all failed. There are the political reasons, business reasons failed too, but ultimately the design point was too limiting. Same for C bus, for those who remember. X10 lasted much longer because all X10 did was turn things on and off and didn't tell you what it did. PSTN, SS7 failed, which is why we have 5G. So there's a whole approach of layered engineering is built for use cases, and we really have to invert that model, think in terms of resources. And behind all this is a longer discussion I can give is the concept of software. The fact we work with abstractions, that none of the physical assumptions about layer dependency make any sense. We send references, not physical things, which means I could ship a truck across the country just by sending the SKU, a part number, and you pick up the latest truck where you are, but that's no different than physically shipping. That's basically what you did in Star Trek, except this time it works. And that's a perfect example. If you say we have to transmit anything in people, you're not going to be able to do a matter transmitter. But if you say we can transmit references, what matter can we transmit? We can do SKUs, we can do physical objects, we can do Amazon. We can find the case that works. So, the intelligence, I won't go through the intelligence of the network. The other concept is networking. We do not need networks as a service. We need networking as an emergent property, just like the road system is not like the railroad. You drive and create your own routes. You create Route 1 by sticking a few signs up. You don't physically build a Route 1. So and each city owns its portion of Route 1 and maintains it. And we don't have a Route 1 provider. In the same sense, we don't need a telecom provider. We don't need a network provider. We need locally owned facilities that we can deposit into a path. So your local Ethernet in your house composites in the path with the rest of telecom. Your city can own facilities that facilitate things. They don't. Now, this is not ownership like a telco does. They're going to exclude. Anybody can add capacity, but it's a very different way of thinking. And that's really what the 5G is the antithesis of. It's what 5G is the idea that you cannot create things on your own. You need a phone company that can do it for you. And we know now from the voice over IP example, from understanding the generic concept of software, yes, we can. You know, Jitsi is another example. People just wrote their own video app. Yes, you can buy the service from Zoom, and there's some nice advantages, but you can also just write your own. And that's very powerful because I can now say maybe hook to Jitsi. I keep saying Jitsi up to OBS if I want. Now, it doesn't mean I can program everything myself. This is the advantage of open source and sharing. It doesn't mean everything has to be shared, but to the extent we can work together and create a community, we can do this wonderful thing. And ultimately, 5G is about the money. If we can't charge for services, how do we pay for the network? And we know the answer: local ownership. You own the wires in your house, so you pay for it that way. And the same way, your community can just own the wires in your city. You don't own them. Again, I want to emphasize, this is not ownership in the sense of being exclusive. This ownership in the sense of work together, support the facilities, let anybody who can add what they want instead. So we get back to this issue of, CT magazine, and it has an article like 5G in medicine. Well, the other story about generic connectivity and medicine. And that's the thing we have to be careful of. There's a tendency to write about 5G as if 5G is necessary. 5G is just the opposite. We need generic connectivity. We might be able to do it despite 5G, but not because of 5G. As an aside, the New York Times had an article by Brian X. Chen on how spotty and bad the rollout of 5G is. And that's because researchers think of 5G as the radios. They get excited. But it's really a MacGuffin for the marketecture of selling you that fast lane network. It's basically a fraud. Come for the radio, stay for the network, and fast lanes, whether you like it or not. So it is. And the other part of it is, there is no real use case for 5G. And that's the thing that's very hard to understand. I think that's the voice example. Look at the examples. Remote VR. Now, first, Avatar wasn't good enough for you. 3D has already collapsed, so we need remote VR. But the other part of it is the reason we argue for remote VR is it works within a single radio. As long as you're in the same radio, yes, it makes sense. You can do these high-speed VR. But extending of the network means ignoring speed of light and all these other issues, and means a brittle dependency, because any glitch, if you do remote surgery and there's network hiccup, it's called murder. You don't want to do that. The other part is you don't want to design applications which depend upon perfectly built out 5G. That's not where the money is. The money is make it work everywhere. So anytime you're dependent upon the favors of the network, you're limiting yourself. Now, there are some cases where you do need very high speed, low latency connectivity guaranteed. And the main example is stealing pennies from widows and orphans. It's also known as high speed trading. But those guys can spend $1 billion running their own private fiber all the way from Japan to New York for arbitrage. So I'm not going to worry about them. But all the other stories are bogus. They assume all the cars can talk to each other via 5G. No, that's a hyper complex version. If we simply have generic connectivity, we can do it better. So basically, and the other, I'll end it with talking about the new literacy. Understanding how you can work without a provider is basically a challenge, because we're taught of intrinsic meaning that this desk of mine is a desk. No, you have to think in terms of, the use that we use software to make something into what it is. A chair is something we sit on. It's not a physical thing. So, and we have to teach engineers in terms of resource rather than layers. Again, I don't want to go on too much into this, but we have to invert the way we think of engineering. So these are my notes at the end, but I think that's, enough for now. So are there questions? And let me see. Oh, it's more questions about OBS, which makes sense. Apparently there is a vibrant OBS community on Linux, but I've been doing it on Windows, so I can't comment on that. But I do want to learn more. I mean, I'm just at the start of learning about OBS. Yes, I can share my slides. I'll share them. Do you want me to share them now? I can just go here to, let's see. Okay, so here, I close down. Okay, sharing link. I'm going into OneDrive. There. Sure. And I can also now go to the other camera. There. And what I'm going to do now, I didn't warn my wife, she's going to appear now. Right off. Okay. So that's without the green screen, so I look normal now. So, other questions? Okay. Frequency, this is something from David Reed. The idea of frequency allocation was, I guess, in the 1930s, the cat's meow is a term you'd use. It doesn't make sense to reserve frequency. It's one of the terrible algorithms. And the way I describe it is, it's like saying there can only be 7 people in a room, because if two people wear the same shirt color, you'll get confused. And we call that confusion interference. It sounds like science, so we have to accept it. I'm going to shut up the other screen now. Okay. So we don't create too much of an effect. So can we convince them? Well, trying. Another important thing here, by the way, for the broadband initiative, we have to make sure that communities can own their own facilities. Right now, the broadband legislation assumes they have a provider. So we need to explain that, no, cities can own their own facilities. This is not municipal broadband. It's a different concept. Because municipal broadband basically is another private telco, just people's telco. What we need is open facilities without a paywall, so devices can just work anywhere. Now, I want to learn more, for example, about Amazon's Sidewalk, so they can do connected devices, but I suspect it's a step in the right direction, but might still have too many limits. Well, there's no interference. Remember, radio signals, at this point, David, do not interfere. They pass through each other. The interference is something that you get confusion if you throw away all the information, you look at only one frequency. If you look at the rich signal, there's no interference. You might be confused if 2 people are talking to each other, but the radios don't interfere. The example I use is when you drop 2 pebbles in a pond, the waves pass through each other. If you use a straw, you just see confusion. But if you look at the whole thing, you just see 2 waves passing through each other. But again, it's not interfering, it's confusion, because all those use single frequency signal. The amateur radios, all these use single frequency signal. If you use ultra wideband with terahertz pulses, you don't get that kind of interference because they pass through each other. So it's a bad algorithm of using tuning forks as the highest technology for radios. That's the source of what we call interference, which is really confusion. And by the way, David Reed, I think I talked to this group about 20 years ago on this. No, it's not a matter of antenna design, because if you look at the MIMOs and all the other things, it's the algorithm of focusing on single frequencies. If you pick up a richer signal and you process it as ultra wideband, you have more chance of basically, getting past it. Or if you can accept our packs, look at how well Wi-Fi does. So even if we don't go, if we stay with frequency allocation, so you take a look at a single wire that would carry one phone call a day, and you turn it to a packet medium, like with DSL or whatever, it can now handle 1,000 calls in that one wire. So if we took all the frequencies and converted to packet medium, even if we kept the algorithms, we still have basically infinite capacity. So it's not for the facilities. It's we need approaches like Wi-Fi, which basically packetize it and use common packet formats and cooperate. Yeah, no, I know that, again, the incumbent service is the problem with anything, which is why we're stuck with it. But I think the problem with it is the reason incumbent services have so much power is not so much of finance and everything. It's because people believe these stories. Because we know that this is a good wire, this is a bad wire. And it's like when Monster Cable is telling you, this modem wire is worth $100, but it can carry 10 megahertz, even when you're going 56K. So it's really engineers, and this is where I cite the IEEE as aiding and abetting, is they're stuck in the old paradigms. They're trying to solve problems inside the network, because there's nothing glorious about just providing generic packets and letting users create their own solutions. So the IEEE is in the backwash of hardware engineering, which require carefully building in each service. That's why IEEE 1394 is such a good example. And they continue to try to basically engineer every element of the system rather than saying, let's assume generic connectivity and a solution, because to some extent they can't. So we need a public policy which should advocate of generic connectivity. Yeah, I mean, there's radar and things that can own some. So even if we cut the slack and say, okay, you can own these frequencies at this power, we could still, there's still so much capacity out there. As Wi-Fi shows, even just getting a little capacity. Also, we don't need a single radio to go all the way across the country. Get on nearest fiber. Then a milliwatts can take us across the country, and the wired infrastructure.
Live streaming is on.
Okay. Try putting, the whole GPS fight and stuff. But again, GPS is another story. We should use, any way of getting information. But I'm willing to say that, if you want, we can try to make sure GPS continues to work and things, because there's so much capacity out there that, again, the comrades packetizing what's available. Take all the TV broadcasts and all that and turn it to common packet medium. We have more than enough capacity to do all the applications. Using the existing technologies. I mean, the digital broadcast transition was a tragedy.
Jerry, I think we should queue up our next speaker.
Okay. I'm going to go mute.
Okay. Jabber, who was our next speaker? Was it Kurt? Were you the next speaker?
Kiran, are you there?
Kiran? I just sent Karan a private message.
Kieran is getting set up right now. He'll be right with you.
Oh, good. Okay.
It might take a moment. While we wait, that Hushbox story sounds pretty fascinating. Is there any more to that?
You hush your phone story?
Yeah.
You can go to Wikipedia and look at it. I mean, there's a whole series of. That story's fascinating itself. You just read about it. I don't have too much to add, but it's the whole history of telephony, basically as delivering a service. And people think of phone. People don't really understand that service-based business. So one part of the story is basically the whole residential gateway, which their future they saw was delivering service to the home. They were going to do e-commerce. I mean, Minitel was a version of this. Okay. And that's why we have Title I, Title II, is because they're afraid of the phone companies getting into the information service business in the same way. And that's why I came into the story, putting the router at the edge of the house to start to give you control of the wires in your house. So this is still ongoing. It's just actually hush your phone as sort of inflection point.
I gotcha. Yeah, it's kind of like it was the first app, and now the phone's turned into an app.
The idea that the phone is an app is still something people find hard to grasp.
Now, I'm curious. So you're obviously aware of like circuit switching, of course.
Like what?
Circuit switching. So like Internet 2, for example, which
you
is
mean Internet 0.5, yes.
Okay. Sure.
No, the problem is a lot of these projects are old recycled telco people. And by the way, most network engineers learned the old network thing, so they think themselves as IP people, but they still think, oh, let's build back in the circuit bus. It's the end of history. We know the applications. So they think they can make it better. I mean, we've seen in database, people build hardware database machines, not realizing schematic evaluation is what brought in the performance. So I see a lot of, I can go into a whole set of other issues of how to make the internet better, the DNS, for example. But for this talk, I'm focusing just on the telco part, which is basically the idea of connected devices and end-to-end is incompatible with trying to make each wire a profit center. And with the telco saying, before you can get the cloud services, we need to make a profit.
Sure. Yeah, don't even look into. There's a lot of work on some of the crypto systems that for IoT, where the devices make exchanges to keep the network maintained.
But no, that's all fine. But you mean the people who want to think bits of physical objects and they want to design for charge for the millibit?
Yeah.
That's like that misses the point. Yeah, that's like virtual gold bugs who think that Bitcoin is real money. I mean, these are people who basically go to physical metaphors for abstract concepts, and that's really my talk on software and why I understand why it's hard to grasp. And I'm trying to figure out how to explain these points. But I see the next speaker is up.
Yeah, thank you, Josh, for that. Sorry about that, guys. My computer having some technical difficulties just now. I appreciate the patience, though. But yeah, I'll be talking about some simulation for quantum computing using Linux and some free open software.
And I'm now the global taskmaster champion, apparently.
Wait, before you start, there's a lot of background noise. Kurt, maybe?
Yep, sorry about that.
Yep, no worries. Yeah, like I said, my name is Kieran, and today I'm just talking about some simulation for quantum computing that I've been doing with Linux and some free open software, open source software. So yeah, just a bit of an introduction and background. Right now, I'm currently an undergraduate research assistant for the Wearable Biosensing Lab. It's a biomedical engineering lab here at the University of Rhode Island under Professor Kunal Mankodia. My research in years prior and partially currently have included smart prosthetics, 3D printing, haptic feedback systems, and even some applications of machine learning. Additionally, in the past and also, well, prior, I was a research assistant, but now I've actually undertaken a special topic research study under Professor Leonard Kahn, who's a professor of theoretical physics here at the University of Rhode Island as well. And my research with him has been evolved from linear optics to photonic band gaps, up until more recently, some introduction to physical implementations of quantum systems and quantum computing and quantum algorithms. So computation is what guides the sciences. In 1981, Professor Richard Feynman at the MIT Physics Computation Conference, he said as followed: the computer will do exactly the same as nature. This is to be proved, and this type of computer is already explained. And it's going to be necessary that everything that happens in a finite volume of space and time would have to be exactly analyzable with a finite number of logical operations. This computer that Feynman was discussing that would do the same exact thing as nature, produce the same probabilities as nature, in this finite number of logical operations. Feynman's credited to, in this scenario, describing the first quantum computer. And funny enough, about 100 years before, Charles Babbage, describing analytical engines or computers as we know it, says as soon as the analytical engine exists, it will necessarily guide the future course of the science. Whenever any result is sought by its aid, the question will then arise: by what course of calculation can these results be arrived at by the machine in the shortest time? So yeah, I guess we start off with what is quantum computing. If you guys can bear with me, I'll talk briefly about quantum mechanics. And if we're not too scared off by that, we can get to some computing, because I know I still don't understand quantum mechanics. I've been doing it for a couple years now. So what is quantum computing? Essentially just the application of quantum mechanics to perform logical operations. These calculations that are being performed using the operations are going to provide a basis of probability solutions for states. An analogy that I've sort of come up with to refer back to, I guess, when we're discussing quantum computing has been the parable of the sock. It's been one of my favorites from my professor of mine. And essentially, the idea is just that we have two sock drawers. They have like blue and red socks, and we separate these drawers like infinite so far. One's on like Pluto on the other side of space, and the other one's in like some other galaxy. And the idea is that, well, first, when we pull out a sock, it's either going to be red or blue. And that is the idea of superposition, or the probability that you'll either get one red sock or one blue sock. In the sense of quantum computing, this would be the probability of measuring a system to be either a 0 or 1. Then comes the idea of if you pull out one sock that's red, similarly, if you pull out a sock from the other drawer that's, say, on the other side of the universe, that sock will also be red. If you pull out a blue sock in one drawer, similarly, you'll pull out a blue sock from the other drawer. This is sort of meant to represent the idea of entanglement. And these are two main ideas that sort of come back to and that we use in quantum computation. So just a bit on classical computing. We know that bits, or classical bits, C bits as we call them, are a state of either 0 or 1, and we use Boolean algebra to perform operations and do calculations. And these calculations, as we know it, are deterministic. So in the sense that whatever input we have will always have one output or one solution for that. And there's a small logic gate and AND gate, but that's the basis for classical computing. Yeah. But in contrast, what would be quantum computing? What does that entail? So quantum computers use qubits or quantum bits, and in contrast to just having a 0 or 1 state, they're one additional thing that accompanies them is their superposition, which is the possibility of being in either state. So just like in the parable of the sock, it's the probability of being in either, or the probability of picking out that red or blue sock. In the sense of the 0 or 1, it's the probability of producing or measuring that 0 or 1 state. So you can see underneath that first line, it's what we know as Dirac notation, which is just a column vector to describe the 0, the 1 state, and that'll be psi. And psi is essentially the summation of the probability of there being a 0 or a 1 being measured. And this summation essentially adds up to 1. Going back to the column vectors that are being used in that Dirac notation, quantum logic sort of comes about with linear operators and is represented through matrix mechanics. So many of the matrices are what perform actions and or take operations. We call them operators on these vectors. And these, when you see them in a circuit diagram, which you'll see later on, will be in the form of gates, just like we have digital logic gates. So like in contrast to classical computers, quantum computers have the superposition, and this is what essentially allows for non-deterministic problems to be solved, meaning that despite having one input, we can have a multitude of outcomes, but quantum computers can allow for the possibility of finding the most ideal outcome out of all of those possibilities. So now I'm going to talk specifically about the actual algorithm that I'm here to talk about, and that's the Bernstein-Vazirani algorithm. This algorithm is specifically designed for determining an unknown or secret number. The idea is like a string of binary digits in a black box that no one knows. You put like any string of like 1s and 0s, and the algorithm will essentially be able to determine what that number is. So classical computers can do this in the sense that if you have, let's say, a string of six binary digits, you have 1 0 1 0 1 0, I think 1 0 1 0 1 0. Yeah, you have those 6 digits. It'll take 6 iterations to actually test to determine what that string is. So essentially, it takes n bits to determine n number of bits to determine n bits for every iteration, I believe, to determine what that string is. In contrast, the Berenstein-Vazirani algorithm will essentially allow to just do one consecutive computation to determine what that string is. This utilizes two universal gates known as the Hadamard and the Pauli X gate. If you look down below, you'll see the gate, the notation, the matrix. As I said before, matrix mechanics is sort of how how we do all of our operations, and it's how we get our solutions. And the Hadamard gate is significant. Hadamard gate is of significance as it puts the qubits into our superposition state, either our 0 or 1. The Pauli X gate is sort of like the NOT gate in that it inverts the qubit. And the C NOT gate is what entangles the actual qubit. So going back to the parable of the sock, we mentioned that when you pull out one sock on one end, if we have it to be red, the other sock in the other drawer that we pull out will also be red. And the same thing here. And this is due to the no cloning theorem that comes about in quantum mechanics, where if we try to measure one system or look at it, so to speak, we won't be able to keep that information. So we can't clone information or copy it as we would in like a classical computer, so to speak. And so that brings a rise to the idea of quantum teleportation, which really only just works for little things. We're not teleporting like ships or people or people to Mars anytime soon, I think. Yeah, that's the Berenstein-Vazirani algorithm. So to do this, I used Qiskit, which is a open source library on GitHub provided by IBM, and I did all my coding in Python in the Jupyter notebook. And the unique thing about this is that although we're able to run it on the classical computers, you can actually send the code itself, if you would like to IBM's actual quantum computer to test it or run it if you'd like. I didn't do anything as extraordinary or unique yet, so I've been holding off on sending my code out. But yeah, the library provides a vast multitude of codes, including the Berenstein-Vazirani algorithm. So here's my demo, just a quick demo of what the algorithm, how it works. So you can see that I have the black box and that unknown number is where it's set at. I just entering a string of 6 bits here. So my string was 101101. My first set of lines of code is just identifying the length of that and then setting up my circuit. And then from there, I index the number of bits. I create a barrier. I implement a Hadamard gate to actually, I'll let the code run. I can go back and explain. So there's a circuit that gets output with a series of Hadamard gates, the C NOT gates, ending the Hadamard gates, and those probes at the end are what takes the measurement. And here's the probability. So we have 100% or a 1 probability that we get that one state at the bottom, which is 101101. And if we go back up, our original number that we put in was 101101. From that. Yeah, so essentially what's going on is the Hadamard gate puts all these qubits into superposition. This second line of code here doesn't quite show it, but all of these, well, at least the top 6, excluding this one with the X gate up here, but all of these top 6 gates are connected to a CNOT. So from there, they're entangled to this one qubit down here. What then happens is as they're all entangled to this one qubit, applying the Pauli X gate and the Hadamard along with the CNOT gate, something called a phase kickback occurs, and this essentially changes the direction of the qubit. And so once you apply the Hadamard finally, and you take your measurement, you'll get a series of plus and minuses that will essentially equate to these zeros and ones that you have in that Dirac notation, or as you saw above. So applications and hurdles. A couple applications of quantum computing have been quantum cryptography. This has been discussed quite a bit, especially with Shor's algorithm, where prime factorization is, for being able to factor prime numbers, is made people fear that quantum computers could hack into everything or anything they want. Additionally, P versus NP problems. This is the polynomial versus non-deterministic polynomial problems. Machine learning and neural networks. Some of this is sort of the idea that being able to run computations simultaneously to one another would, in the hopes, speed up machine learning and neural network computations. Some of the drawbacks, however, that we're still experiencing are decoherence and the actual physical limitations of our systems. So decoherence is a problem. I think just before I started talking, we were discussing about how it doesn't matter, but waves will essentially interfere with any computation, especially when we have such a small system. Most of these are using something. Well, this also relates to the physical limitations, but electrons are easily manipulated by any sort of electromagnetic vibrations. Vibrations are just any sort of wave that can interfere with the computation will at some point. But also the actual physical limitations with between quantum optics and superconductors. So IBM, I believe, uses a superconductor-based system, but the problem is this thing is literally like a giant fridge in order to actually do computations, and this giant fridge that holds like 80 qubits or something like that takes up the entire room, which is not convenient. Not as much of a similar problem with quantum optics, but it's just the problems with entangling photons. Not so much of a space problem, but more of a still tacking behind how to actually get it done, more so. And that is all. Currently, I'm still doing research in quantum optics, pretty interested in applying physical systems to do quantum computing. I've just recently, essentially everything you guys have seen so far is up to my coding capabilities for these types of problems. But I've become quite interested in applying these codes for cryptography methods. And relating back to the physical systems, I've just been researching superconducting systems for quantum computing as well.
Okay, thank you, Kieran. Kurt?
Yeah, actually I see a couple questions here. Can I scale my example to 128 bits?
I think he means, does he mean qubits?
Oh, yes. If I'll go back here. I believe so. These top 6 actually, so these top qubits, could I scale that to 128? Yeah, you definitely could. Can you scale? Yeah. Yeah. It's more so just the idea that, oh,
But is that hardware realistic with our current level of technology?
yeah, I see what you mean. I'm not sure. I think the max you've gotten in terms of like qubits has been 80. Qubits and bits don't exactly work the same way though, so I'm not sure if those have the same limitations. I'd have to look into that more. That is something definitely worthwhile looking into. Thank you for that. I suspect we are years away from a production quantum computing, but do we have a similar academics we can use remotely? Yeah. Actually, I found a really good simulator yesterday that you can literally like instead of just like coding out your circuits like this, you can actually see how each gate will affect the outputs and how it relates to the actual quantum mechanics of the problem. So I can find that again. I can drop the link for that as well.
So Jerry, we only have possibly one last speaker, and that's James. Although it's probably 4 a.m. in Spain, so maybe he's dropped off. James was going to give us an update on, I think, his mesh project. But thank you, Kieran.
Thank you.
Yeah, thanks. James, you around? Are you awake?
Oh, he might have logged off.
Yeah, I don't see him online. He was on earlier. We lost a couple of people.
Anybody else have a lightning talk?
I guess we're all set here.
I'll get my slides together for the next. I don't think I'll try to insert it into the next month Jabber, but I'll get something together probably as a read ahead, maybe a YouTube read ahead for the for either Steve Herrick's videos or an overview of the 900 megahertz spectrum. We're overdue for that. I think I did that about 6 months ago. So yeah, that'll be a good thing to do. Not next month, but maybe 2 months from now.
Right now we're full up through January, so February is really the next opening.
Okay.
Yeah, so we can plan for February. So I'm going to go ahead, unless there's anything else, I'm going to go ahead and stop the video live stream.
Okay.